So this is going to be the walkthrough for k-means. We're going to look at a data set which is probably not the nicest data set in the sense that it's data about all the states in the US, and then it's got rates of crimes for various different types of crimes, murder, assault, etc. For each of those states. What we're going to try and do is see if there's any patterns in the crime rates over each of the different states, see if there's groupings, and then we're going to visualize the results. So a nice simple application of k-means, how we cluster this data to see if there's any patterns in it. So no labeled data, unsupervised learning. So let's do this. Okay, so first of all, we're going to do our standard import of our packages. So numpy first, pandas next, and then a couple from scikit-learn. Okie dokie, and we will do another plotting one later. Right, so first we've got a data set, we're going to upload it. So we do pandas read CSV, use autocomplete. So the file we got, which is you can download as well, is called data arrest. In this file, the delimiters, so the things that separate the data, are commas. So we'll tell it that. We'll also tell it that the index column is the first one, and that's actually going to be the state. So that should do it. Hopefully that works. We can then look at the head of this data. Okay, so this is the first 5 lines. As you'll see, we've got each of the states, index column, then crime rates for murder, assault, urban pop, I'm not sure what that stands for, and sexual crimes. Very cheerful topic, unfortunately not. But okay, so what we will then do is we're going to build our clustering algorithm. But as we discussed in the practical side, or the theoretical side, or the walkthrough side, normalizing your data with k-means is really important. This is because you're taking distances from the centroid. If your components are scaled differently, then you'll bias the results by one feature having more importance than the other. So it's really important to rescale your data. So we're going to do this from scikit-learn, some pre-processing, and then we're going to use min-max scaler. So, and then we will, so it's a class, so min-max scaler, we'll use it again later, so we're going to call it something. So this just means initiates the class min-max scaler. We're going to make a new data frame, so we'll call that hat data frame, and then we'll call it, okay, so PD, make a data frame, and then we will do min-max fit transform data frame, and then we will look at this. So what this is doing, calls a package min-max scaler, makes an instance of the class min-max data, then it makes a new data frame. What we've done is we've taken min-max and we've fitted it, we've done a transformation of the original data frame. So we should now have a new data frame hat df, where we will see what's in it. So now instead of lots of different numbers, all of them are scaled between 0 and 1. So if we look at the scribe, which tells us, what we will see is each have 50, so there's 50 states, and where's min-max values? So min values all 0, max values all 1, and they have a distribution in between. So all the parameters are now nicely scaled between 0 and 1. Perfect. Okay, now we've done that. So we're going to do the elbow method. So what you remember with that is when you're not, it's not clear because you haven't looked at the data yet, how many clusters to choose, what you do is you build a whole series of k-means models for increasing number of clusters, and then you make an elbow plot. So we'll do that, and then we'll look at the plot and see how we derive how many clusters we're actually going to use for the analysis. So sklearn has many things, and of course one of them is k-means. So we're going to make a plot here. Fig size 8.6, that's like rectangle, and then for I in, so how many are we going to do? We're going to go from 1 to 10, so it always runs to 1 less than the top number. So the model is going to be called k-means. It's going to be k-means. The number of clusters is the parameter n clusters, and we're going to give it I. So when this thing loops through, it will do 1, 2, 3. So we'll build models for each. Init is just a way of initializing those centroids. So we're going to use k-means. It's going to try a number of initializations, but we'll let it pick its own. So we'll call auto. Don't worry about these parameters so much. And then we will give it a random state so that each time we run it, it will run the same thing. And then we just have to give it the data. So fit hat df. So we now want something to hold the inertia. So remember, the inertia is sum over all the data points. It sums the mean square distance to each of its centroids. So whichever cluster the data point lives in, it calculates the distance to the centroid of that cluster and sums them all up. So basically a very low value means very clustered data. So we're going to take inertia, we're going to amend to the list so we can plot them, and then the model has something called inertia like this. So k-means is a fitted model. K-mean, this is a class we've called fit. This is now a trained model, and then we've evaluated the inertia. The underscore here means that it's a variable that only gets assigned once trained. So it would be empty before the model had been trained. So we can now hopefully plot from range 1 to 11. Give it a title. Just check that I've got. Ooh, that's not going to help. All right, let's rerun that one. Let's put that here as well. That certainly wouldn't have helped. Okay, yeah, so I had a squiggly line under plot, which means that it didn't recognize this module that I tried to load in. Right, here's my plot. So we'll remember what we see with the elbow method. The inertia goes down as we increase the number of clusters. It's kind of obvious. When the number of clusters equals the number of data points, every data point is its own centroid, and so this thing goes to 0. What we're looking in the elbow method is essentially a transition in the gradient. So the largest or the steepest gradient is dropping really to 4, and then we've got a much shallower gradient after 4. So this suggests that sort of the balance of sort of having lots of clusters and reducing inertia versus trying to cluster things as much as possible, the balance between this is probably achieved at a cluster number of 4. So let's rebuild k-means model for 4 clusters. So let's do, so our model is going to be k-means. We've chosen N4 as the clusters from the elbow method. This is the same as last time. Auto. I'll pick the same random state. Okay. and then the number of clusters is basically model fit predict hat df. So it's now going to return the number of clusters. We're going to do a scatter plot. So we're going to just plot the first two. So we'll do murders against df assault. Very pleasant data set. And then we will set the colours of the scatter to be the clusters. So hopefully we'll see some clustering. And then we'll have plot k-label murder rates, plot y-label assault rates. And let's have a look at this plot. Yeah, so clear clustering, yellow's down here, blue in the middle, lighter blue, and then yellows towards the top. Bit of overlapping, but it's kind of expected with a projection of the data. They wouldn't be overlapping if you looked at them in 4 dimensions. Right, so that's kind of done, you could say, but how do we draw insight? It's actually more helpful to look at this on a map of the states of the USA and see if we can colour each of the states with the different clusters. So I'm not going to go into too much detail here. So there's a really nice package which you can import. So Plotly Express. So to do this, you can install it using pip. So let's just put that. So you can install this using pip install. What's the? It's Plotly Express. Okay. So if you put this in your terminal and then reload your kernel, you'll have this package. I'm then going to quickly nick a list of US states to their abbreviation, because in this package they don't take the full name of the state, they take this 2-letter abbreviation. So we will, I missed out that should be nice now. Yes, right, fine. So this is just a dictionary lookup. We're going to have to manipulate the data a bit to be able to get the plot. So let's have abbrev states. And then for each state in the index column, which is the words for the states, abbrev state, we're going to add one to the list. We're then going to use this dictionary US state to abbreviation that we've just loaded, and then we're going to put lookup state, so that should convert the two. We're then going to add this to our data frame, and we are going to add the clusters as well. You'll see why in a minute. Okay, so let's just have a quick look at that to make sure it looks good. Okay, so we've got our original data set, we've got our text, our full words for the state. We've now also included this state code, so we've basically looped through each of these. We've looked up Alabama, then looked up Alabama in this list and taken the abbreviation from this pre-saved list. And then we've also added another column called clusters, which has come from our 4-cluster k-means model that we've just trained. So the next bit in Plotly, you have this nice function called choropleth. Not very good at saying things like this. It's a type of plot of a map, which is very useful in visualization, particularly of state data. So it's going to have a data frame. So the locations are going to be, what have I called it? I've called it state code. And then there's an option for location mode. Is that one word? Yeah, location mode is. USA states. So this is just an option. You can look at this function on the web. Scope is USA. So these are just map settings. Color is going to be clusters. And then what we're going to have color, continuous, scale. You can pull a particular color map, which one did I pick before, just so it looks the same in the notes. Viridis, I think. So looks like something's not happy here. Yep, didn't read that. Okay. So when I call this, so what's going on here? Argument I think I've missed a U in continuous. And it would help if I put fig show at the end. Let's do it again. There we go. Fine. So what you have is obviously a map of the United States, and we've coloured each of the states according to their cluster. So you can see distinct groups, actually spatially correlated in particular regions. I'm not going to draw political insights into which are which, but one of the interesting things you might do is then look at the centroids of these clusters and see if they have particular characteristics. We need to take our centroids. So in my model, I will hopefully have cluster centers. Yeah, so let's have a look at those. Okay, so this is then a numpy array, which describes each of these clusters. So each of these vectors describe the clusters. Problem is they don't mean a lot relative to the original data because they've been rescaled between 0 and 1. So you could kind of look at relative things, but it'd be more helpful to rescale them back. And to do that, we had a min-max scaler, and we did from, say, min-max inverse transform model cluster. Right. And so what this will do, hopefully, is it will scale it back into the same scalings that the original data set was in. So if we do this, and then we remind ourselves what the original data set looked like. Okay, so what we're really looking at here is in this first cluster, we're seeing that the first cluster, okay, the third cluster, so label cluster 2, and this is 0, 1, 2, 3, because we start counting from 0. The third cluster is essentially low murders and generally low crime relative to all the others. Right, so that's the place we want to live. So 2, so that's these states up here. It's up near Boston, or so yeah, all the blue states are the lowest crime. Let's look at another one. So what's the sort of California down Texas? That's cluster 1. So that's this state. So much higher murder rates, and then the highest sexual assaults. And then the final one, so let's have a look at this one, the highest murder rates, that's associated with cluster 2, cluster 3, and so that's this band in the middle here. So as I said before, in Alaska, so I'm not going to draw any insights into why each of those, but what you're seeing is that from the data, you're seeing that you can pull out information or similarities within that. This data has no information about how close those states are, but it's interesting that the clusters pull out some geographic correlation. So this is really, so K-means is a useful, easy tool to be able to start exploring correlations or connections or similarities, patterns in your data before doing other analysis or interrogation of them. So yep, this is the end of the k-means. Hope you found it useful. My recommendation is you look through this one, you run it yourself. It always helps to type it out as well. And then go and find another data set, hopefully one of yours, or lots of good examples online, which we'll try and post some good examples that you can try it out yourself.